Sir, is it audible, sir?
Yes, madam, it is audible.
Okay, thank you,
Possible
sir.
switch on your camera. Possible switch on your camera.
Okay, sir. Sir, I have.
Okay, madam.
Yes, ma'am. Yes, ma'am.
Oh, okay, sir. This is Padmalata, Assistant Professor of AC Department, Kudlala Engineering College. It's my immense pleasure to introduce today's speaker, Dr. Mrinal K. Mandal, sir. So, Dr. Mrinal K. Mandal attained BTech and MTech degrees from the Institute of Radio Physics and Electronics, University of Calcutta in 2001 and 2003, respectively, and PhD degree from the Department of Electrical and Electronics Communication Engineering, IIT Kharagpur in 2008. From 2007 to 2009, he worked as a research fellow in the Institute for Infocom Research Agency for Science, Technology and Research, Singapore. He also worked as a postdoctoral fellow in the University of Quebec in Montreal from 2009 to 2010, and in the Polytechnic School of Montreal from 2010 to 2012. He joined IIT Kharagpur as a faculty of Department of ECE in 2012, where he is presently serving as an associate professor. Dr. Mandal is a senior member of IEEE since 2013. He is in the editorial board of Wiley International Journal of RF and Microwave Computer-Aided Engineering. He was in the board of organizing committee members of several international conferences, including Asia Pacific Microwave Conference 2016. He obtained MHRD's national scholarships for excellence in secondary and undergraduate examinations. He has authored or co-authored over 110 journal and conference papers, including 40 in different IEEE journals in the domain of microwave and millimeter wave circuits and systems. He has also filed 11 patents. His present research interest is co-design of active and passive components and their design and their application in reconfigurable antennas, millimeter wave imaging systems, beamforming networks, Doppler radars, and 6-port receivers. With this brief introduction, I would like to invite Dr. Mrinal K. Mandal, sir, to enlighten our minds with his session. Sir, please welcome.
Yeah, thank you, madam, for your nice introduction. So
Thank
let
you,
me
sir.
share my slides. So is it visible to all of you in full screen mode?
Yes, sir.
Yes, sir. It is
Okay, thank you. And good morning to all of you. So today, mostly I'm going to present on different design challenges at millimeter wave frequencies. And more or less, it will be my presentation flow. So I would start with some common problems which we frequently face at higher frequencies. So particularly at higher microwave frequencies and millimeter wave frequency range. Then I would continue with a type of materials popular at millimeter wave frequency range. So here actually we have several issues. So what type materials is ideal for the given applications at millimeter wave frequency range? So we need to consider many other points as well. Then another problem frequently come, it is actually the most important point, I would say, at millimeter wave frequencies, that in general, power loss increases. Then we need to first know about the sources of loss. Then we can work on it, how we can minimize different sources of loss at millimeter wave frequencies. Next, high frequency limitation of the popular guides. So particularly due to higher modes, and another point, of course, increased loss. So when we go for then design for a component, it can be passive component, active component, or co-design of passive or active component. So we face some common design challenge. Then how to simulate that? That is also another problem. Then finally, when we go for implementation, we need to consider the fabrication facilities. So we cannot go beyond that. Otherwise, let's say we come up with a structure which nobody can fabricate. So it won't work. Measurement is another challenge at millimeter wave frequencies. And some people working on millimeter wave systems or maybe on MMIC or RFIC technologies. Then for interconnects, these interconnects, it can be from one device to another device or from one component to another component. So basically we have then two parts. One is inside the chip, what type of connection we should use, and what for outside the chip when we go for system integration, particularly using some PCB type substrate material. Finally, we need to package it. So packaging creates also other issues. And if time permits, some problems due to propagation at millimeter wave frequencies, I tried to cover it. So let's start with the first topic, some common problems at higher frequencies. So here, I'm not going to introduce any new term. You already know all these terms, but what happens at lower frequencies, sometimes the problems because of this is so less that we simply discard it. One example is surface roughness. So if the RMS value of surface roughness, if it is comparable to skin depth, then suddenly metal loss increases. Now, usually the skin depth, it is much less at lower micro frequencies. And when we go for simulating any structure, let me give an example of passive beta, because most of you are doing design of passive components. Then in HFSS or CST, you recall, have you ever introduced the surface roughness? Most probably not. You consider smooth surface. And that will provide good result. In fact, measurement result will be very close, like your predicted result by the simulator. But that is true at lower gigahertz frequencies. Now, if we go up to millimeter wave frequencies, about 30 gigahertz, or let's say you are designing a radar circuit for 77 gigahertz applications. In that case, you cannot discard this surface roughness. Then your measurement result will be different. You will end up with very high loss. Actually, you did not model the surface roughness in your simulator. So this type of problems are there. So we are not learning any new terms, but we need to revisit through all these new all these terms, and we need to consider their effect. Is it significant, or we can still discard it at high frequencies? So let me start with the first term, phase constant. So phase constant, how we define? Change of phase per unit length. So if I have one wavelength long guiding structure, then because of one wavelength, I have a change of phase of 360 degrees. So then phase constant, this is equal to 2 pi by lambda. Now, obviously, in free space, lambda is lambda naught. If we have dielectric medium, lambda is something different. Most of the time, it is lambda by square root of epsilon r. But if it is a guided structure, then it is something different. For one air-filled rectangular waveguide, usually this lambda g is more than lambda naught. But whenever we consider any dielectric field guiding structure, it may be rectangular waveguide, it may be microstrip line. So for them, usually lambda g is less than lambda naught. Now this, if I do not want any dispersion, then this variation of lambda or variation of phase constant with frequency, it should follow a straight line. If it deviates, that means we end up with a dispersion. Not only that, when we are connecting, let's say, antennas in a antenna array, I have several radiators, and from the power divider, I'm connecting each of the antenna port. Let us, for simplicity, consider 1:8 array, and you are connecting with 8 cables to your power divider. Now, the length of each connecting cable should be equal, but practically it is not exactly equal. There will be some difference. So how much difference you can tolerate? That is directly related to phase constant, beta. So here, for example, I considered, let's say, silicon with a dielectric constant of 12. Then if I calculate lambda g, it comes 1.44 millimeter at 60 gigahertz. So that means if I have an error of 100 micrometer, it's not huge, just 100 micrometer, that will introduce 25 degree of additional phase, and we don't have beam alignment. So instead of 60 gigahertz, if I repeat it at 6 gigahertz, then but due to this 0.1 millimeter difference, we have just 2.5 degree. That in most of the cases we can simply discard, but here it is not the case. Similarly, skin depth. Skin depth definition, all of we know. So here, for example, for copper, at 50 hertz, skin depth comes 8.5 millimeter. At 10 kilohertz, it decreases to 660 micrometer. Now, it further decreases to just 0.21 micrometer at 100 gigahertz. And we face problem. So first of all, we know that this is the reason why we cannot use a single metal wire for gigahertz power transfer. But if I look at our 50 hertz source in our room, so switchboard to tube light or fan or refrigerator, we are basically using single wire. So in that case, we don't have as such any problem because skin depth is 8.5 millimeter. Now, if I plot current distribution over the cross section of the wire, it will be uniform. But if I do the same thing at gigahertz frequencies, it won't be. The current, it is mostly concentrated on the surface. So it looks like a filament, and that's why surface resistance, it increases. And this is the reason why we cannot use a single wire for power transfer even at lower gigahertz frequencies. Now, from these relationships, we have another interesting observation. So J, it is equal to the surface current density into e to the power minus d by delta. Delta is the skin depth. So as we go down inside the conductor, it decreases exponentially. Then when we are going to implement any PCB, so what should be the minimum thickness of copper or gold? Because after sometimes no electromagnetic wave exists inside metal, no current. So thumb rule is we take it at least 5 times of the skin depth at the lowest frequency of operation. Since at the lowest frequency of operation, skin depth is highest. So if I take at least 5 times, then it reduces to less than 0.1% of JS at the surface. So for PCB material, it may not be a problem. Now, if I consider RFIC fabrication or MMIC fabrication, so in those cases, typical metal thickness, they will be using 1 micrometer or 1.2 micrometer. So 1 micrometer or 1.2 micrometer, it becomes almost comparable to skin depth at in the X band. And at higher frequencies, we have again the same effect. Now here we face another problem because of this. So we know that any metal or any wire, current carrying wire, it is associated with self inductance and self capacitance. Now when current is uniformly distributed over this cross section, for example at 50 hertz, then we have closed form expressions for the self inductance and self capacitance. So we are mostly worried due to self inductance. Because of this, signal is highly attenuated and phase also changes. And at higher frequencies, when skin depth is much smaller compared to diameter, we have this type of current distribution. So again, we have the closed form expression. Now, what happens in between, in the transition region? So in the transition region, actually this inductance value, self-inductance or self-capacitance, it varies very fast. So one condition we call low frequency condition, when the current is more or less uniform over the cross section. Another condition we call high frequency condition, where current distribution looks like this. But in between, this inductance per unit length or capacitance per unit length, it changes fast. And without doing full wave simulation, it's really difficult to say what should be the equivalent self-inductance or self-capacitance. So this problem will be facing mostly when we'll go for RFIC or MMIC design. So that's why above X band, they start facing problem, and without any EM solver, they cannot proceed further. It is true for RFIC engineer as well as MMIC engineer, particularly at lower millimeter wave frequencies. Third point is the group delay. So group delay usually we define when we have some amplitude envelope. So that means it is associated with many frequency components. If I consider a monochromatic wave with a single frequency, then we use better the term delay. So anyway, if I have a two-port component or even a section of guiding structure, so then this electromagnetic signal, it takes some time to reach from port 1 to port 2. Now, if I plot this delay versus frequency, and if I want no dispersion, then it should be a straight line with zero slope. So all the frequency components, they should take the same time to reach port 2. But practically, all the guiding structures, they are dispersing. So basically this delay, it is time dependent. And if we consider a two-port device, so for any two-port device, you can take example of filter or even coupler, power divider, anything. And that is also true for active components, amplifier. They are associated with some bandwidth. Now, what happens at the transition? So pass band to stop band, left side. Similarly, right side, pass band to stop band transition. So at this card, basically. So at what happened there? Input impedance, it changes fast, right? So when the input impedance is matched to the system impedance 50 ohm, we have the pass band. And when it is close to zero or very high, infinity, then we have high reflection from port 1, and that will be out of band. Now in between, this reactive components, it varies very fast. And any reactance, basically it is associated with energy storing element, capacitor, inductor. So that's how we can also explain it. So this change in impedance, it is always associated with change in phase. And because of that, delay also increases. So change how we define delay, it is minus del omega of phi, where phi is the transmission phase. So if we can measure S21, then it is minus del omega of angle of S21. Now at this band edges, where the reactance is changing fast, In those cases, phase change of phase with frequency, it is high. So that is why delay is high. So it is a very common phenomena that at the band edge, our delay will be high. This is true for all passive components, almost all, except a few, and most of the active components. Now, another issue. If we have multiple modes propagating through the guiding structures, or sometimes what happens at the discontinuities, we can have higher order modes. So what is discontinuity? So if I use some impedance step, low impedance to high impedance, that transition we call a discontinuity. If I use one open circuited stub or short circuited stub or even a junction, so you can even in fact plot the electric and magnetic field at the discontinuities, and you will see that it is not exactly looking like the desired mode. For a microstrip line, for example, we know that it is quasi-TEM, and the relationship, how the electric field distribution or magnetic field distribution over a cross section it looks. Now you repeat it for a junction or a simple 90-degree bend, and just at the bend you define a cross-sectional plane and plot the electric and magnetic field vector distribution, vector field distribution, and you will see that it is not exactly looking like the EM mode. So it is associated with higher order modes. Now, what is the problem with this higher order modes? So first of all these discontinuities, because of this higher order mode excitation, they will provide change in phase. So this is associated with some change in delay. And another problem comes, all the different modes, they are associated with different phase velocities. So if we have multiple modes inside our guiding structure, then we end up with dispersion. So energy will be distributed among these modes, and at the correcting point for two, they will reach at different time, and then it will distort the signal. So these are some common issues, and at millimeter wave frequencies, actually excitation of higher order modes are very easy. So we'll come to these points later. Now, some general characteristics of the for the guiding structures. Well, so we know all the popular guiding structures. For example, coaxial cable, rectangular waveguide, microstrip line, or CPW line, last two PCB-based structures. So can we still use this guiding structure at millimeter wave frequencies, and particularly at higher end of the millimeter wave frequencies, above, let's say, 110 gigahertz? So we have some serious limitations, and we'll see later. I'll discuss these points in details. So we'll see later where at terahertz frequencies, we only left with one option, rectangular waveguide. We cannot use coaxial cable or CPW line or microstrip line. So for any guiding structures, then what is the utilization of metal? We were discussing that we cannot use, or we try to avoid metal for high attenuation, but we need to guide the electromagnetic wave. It should not radiate. So for that only we use metal. But the moment we introduce some metal, it is associated with conduction current, JS. And in fact, we can calculate this conduction current component on metal. How? If I know the tangential magnetic field component, then we know this relationship, N cross H, that is equal to JS. So this N cap, it is the surface vector direction. So N cross H tangential, it will give me the surface current, and on the surface it is highest. So then looking at the tangential magnetic field, we can estimate about JS. So the conclusion from first line, that we need to try to avoid high concentration of magnetic field, particularly tangential magnetic field on the metal surface, it will create a problem. Let me give one example, rectangular waveguide. So for a rectangular waveguide, if you think about the TE10 electric and magnetic field distribution. So magnetic field, it forms loops around the electric field, right? Now on the top wall or bottom wall, it becomes tangential, and on the side walls, again it is tangential because it forms loop. Now, if you look at the magnetic field intensity, tangential magnetic field is highest on the top wall as well as on the bottom wall. So we have higher Js. So Js also in some of the textbooks, it is plotted. So that is why this surface current is high on top and bottom wall. On the side wall, it is vanishingly small. So mostly then we face with the conduction loss, it is coming due to from the top wall and the bottom wall. But from the side walls, it is negligibly small. Now, how we can avoid it? How we know the reason? How we can at least minimize it? We cannot avoid it completely. We can increase the height of waveguide. So if we increase the height of waveguide, basically the width of the side walls, I'm saying, then automatically electric field, magnetic field intensity will decrease for a given power. So that's how Js will decrease. And Js is one of the most important thing because heat loss is proportional to square of the current. So that's how we can decrease loss. So we need to revisit all these terms like this. We are not going to discuss any new theory as such. So all the basic theorem, it remains same. So then at higher frequencies, we need to characterize it with respect to how much attenuation it is providing per unit length. How what is the power handling capability, particularly for high power application. And another important point, which mostly we don't consider at microwave frequency range, what is the monomode bandwidth? Means over this bandwidth, the guiding structure itself won't support any higher order mode. So even if it is excited at the discontinuities, so it will die out. It looks like evanescent mode. So of course, all these terms are frequency dependent. Attenuation, it does not remain constant. We know that attenuation, it increases with frequencies. Well, so effect of surface roughness, and we discussed these points already. Excitation of higher order modes. Then cross-sectional area. Yes. So this cross-sectional area, again, let me give one simple example, then it would be better to understand. We have coaxial cable. We use them frequently for any measurement with the VNA or spectrum analyzer or with your RF source. So its main advantage is that it is flexible. We have a flexible form, so we can also twist it easily. Now, for this same 50 ohm, you might have seen coaxial cable of different diameters are available in the market. So which one would provide me high power handling capability without doing anything? We can actually say that the cable with higher diameter will provide high power handling capability. Why? Again, the same reason. So let's say I'm sending 1 watt of power through a very thin coaxial cable. Another one is thick. So for the thin one, if I calculate the electric field intensity, magnetic field intensity, then it will be higher. So the corresponding losses, like the conductor loss, then inside the dielectric loss is proportional to electric field. So dielectric loss, they will be high for the thin one. So thick one will be better with respect to power handling capability. So in fact, the attenuation also, we expect for the thick cable, it is lower. Fabrication tolerance. So finally, when after the design, we need to implement it. So particularly fabrication tolerance. This term is important. Okay, let me give one numerical example again. So we have one PCB milling machine, and the specification for tolerance is given plus minus 25 micrometer, which is a very good value at microwave frequency range, particularly X band and below. Now, how much is it? Because of this tolerance, let's say I am designing one rectangular cavity or a microstrip line resonator. Now, if the length varies, then corresponding resonant frequency will change. For a microstrip line, if the width changes, then its characteristics impedance will change. Now, how much change in characteristics impedance or how much change in resonant length we can tolerate? So that we need to first calculate, and we need to check it with the available fabrication facilities. So plus minus 25 micrometer, it will be very good actually till X band. Now, if I want to design something at 24 gigahertz, we need to be careful, or 30 gigahertz, because now we are dealing with a frequency 3 times more. So theoretically, then if it is 0.025 millimeter for X band, then similar effect, if I want to bound myself within the similar effect, it should be 25 divided by 3 at 30 gigahertz, but which is not supported by the instrument. So that is why we need to check again before starting my design. Can I fabricate here, or I need to set somewhere? Or in some cases, it is fabricable at all or not. That also we need to check. So fabrication tolerance, it becomes another important issue. Cost increases with this. Well, so here I'm showing some millimeter wave circuits. So this right hand side part, actually, these are all 24 gigahertz design. And we designed here and fabricated using our in-house component, in-house fabrication facilities. So this is a RF unit of a 24 gigahertz Doppler radar. It is actually a multi-layer PCB fabrication. And I'm showing only the topmost one, which consists of the main RF chip and the other side antennas. Antennas, actually, you are using a superstrate on top of it. So it is, you cannot see this antenna properly. So we have a dielectric coating basically on the antenna. It is 2x2 array antenna for the transmitter, 2x2 array antenna for the receiver. Now, in the second example, these are again antennas, but here the fabrication is not that great, but even though we got very close to the desired result, it is 2x2 slot array antenna in SIW technology, basically. Now, left-hand side, it is one MMIC amplifier from Corvo, and bottom left, it is a 77 gigahertz radar. It is now available commercially in market. So what we see, particularly when we go to millimeter wave frequencies, can we still use PCB, printed circuit board? You need to check it. Not that we cannot. At least at 77 gigahertz, with some limitation, we can still use it. But when you cross, let's say 110 gigahertz at higher end of the millimeter wave frequencies, so the use of PCB material, it becomes questionable. So in most of the time, what people do, you see, if we can integrate all the RF front end in one chip, then I don't have to deal with the millimeter wave frequencies outside the chip. So what I mean by the front end, so from antenna to for the transmitting side, I have next power amplifier, some filter, then mixer, then low frequency component. For the receiver side, first low noise amplifier, there can be a second stage, filter, then the mixer. So before mixer, it is low frequency component, so we don't have any problem. So if we can integrate everything inside a single chip, then we don't face any problem. We can still use traditional PCB technology for integration, because in the PCB we are not dealing with the millimeter wave frequency components. So it is gigahertz or even sometimes megahertz components. Now, on chip antennas, people still struggling with the antenna efficiency and gain to maintain. But the common practice that people will be using off-chip antennas close to the chip. So for this 77 gigahertz radar, actually you can understand it is having two receiving antennas, one transmitting antenna. They are using one array, and only these pins are dealing with millimeter wave frequencies. So they are using a ceramic based material, a separate PCB for this millimeter wave frequency range. And after that, they are integrating all the components, including the low frequency components, then the DC power distributing unit, and some basic signal processing unit, everything in one PCB. So that's how actually people doing it. Now inside one MMIC, here I'm showing just amplifier. So it looks like one microstrip line based circuit. So we'll discuss about this MMIC and RFIC later. So we at 24 we can do it, but even 24 gigahertz, it actually according to textbook definition, it falls in microwave frequency range. But it is very design principle or whatever we are following here, it is very close to millimeter wave. So we still need the concept of or the design challenges of millimeter wave frequencies we need to learn. Otherwise, we cannot directly go for a 24 gigahertz design. Well, so since we are discussing about MMIC and RFIC, and most of the components at millimeter wave frequencies, people will prefer these technologies. There is a reason. I'm coming to that point later. So let us discuss some basic points about this MMIC and RFIC fabrication. So it may not be, you may not be familiar with this. So if we look at different fab labs, we have mostly these four parallel technologies. First one is in general we call group 3, group 5 technologies. It is always a compound semiconductor. These semiconductors are for different purposes. For example, gallium nitride people use for high power application. Gallium arsenide or indium phosphide people will be using for high frequency application because here mobility is higher. Then the silicon germanium technology. Here, people use high resistivity silicon. We discuss what is high resistivity silicon. And the third one, which is actually the most popular technology, it is CMOS based technology. So they are using MOSFET inside, PMOS and NMOS. We prefer NMOS because of the higher mobility of the electrons. Now, if you look at different chips available in market, more than 90% chips are digital chips based in CMOS technology. So they already have $1 trillion market. And for this RFIC technology, which has, let's say, $1 billion market, they are not going to change anything. Whatever facilities available from the fab lab, we have to use. And we face many problems. So if possible, if time permits, we'll be covering some of these points. So this CMOS fabrication process, it is optimized for digital circuits. So it's not good for RF frequency or this gigahertz frequency applications. Now the fourth one, it was old technology. And here actually it is BiCMOS. So it's a combination of BJT and MOS circuit. So they don't use direct BJT, HBT. And so these high frequency millimeter wave components, they will be doing using the HBTs, and the low frequency digital circuits, they will be doing using CMOS technology. So recently, again, it is becoming slowly popular. So in fact, the amplifier with highest frequency of operation till date at terahertz frequencies, people could fabricate only by using this technology, BiCMOS. There is no alternative. So if you want to design some active components like mixer, there are some other parallel technology. But for like amplifier, low noise amplifier, there is only one technological option above 300 gigahertz, that is BiCMOS. Now, if you look at the fabrication process, they are different. So in CMOS technology, they start with the bulk lightly doped P-type or N-type material. So that bulk material I did not show here. And in the very first layer, they'll be fabricating the devices. And then it is oxide, metal, it goes like this. So why so many metal layers? These are only for connections. So you consider the breadboard circuits we used in our UG lab. Just to implement one, let's say, cascode amplifier or any two-stage amplifier, how many wires you had to connect? And now consider they are going to fabricate millions of devices in 1 square millimeter. So how many connections they need? So that's why they reported all these layers just for interconnections. And the thickness of this typical metal, it is 0.8 to 1.2 or 1.5 micrometer. It varies from technology to technology, from company to company. At the topmost layer, it is always the thickest layer. So for this particular Fab Lab from Fujitsu, they are using 7 metal layers. In fact, for high-speed digital circuit or for some complicated circuit, it can go up to 20 layers, 20 metal layers. So what we see here, it is a vertical step-by-step procedure, layer by layer. But if I look in the this group 3, group 5, it's completely different. So it starts with some wafer or base material. For this example, they used silicon as the base. We can in fact even use metal as the base or some other dielectric material as the base. Then a thin layer of separator, then the gallium arsenide layer. Then it is actually for hemmed gate fabrication, or we can have our metallization directly. So it is a single layer process because gallium arsenide, it is only dedicated for RFI high frequency applications. So we don't need that many of connections. So here, obviously, performance will be better. But again, we have some other issues. Those we need to take care. Well, just in short, then after chip fabrication, what happens? Can we directly use it to PCB? It is not. So we need to go through packaging for weather protection. And so it is not a single step procedure. So here I started with a simple example of a diode and a resistor. So at low frequency, these diodes we used during our UG labs. So this die, PN junction, actual die, it is in micrometer. It sits on a metal base, and then from left side or right side, they use wire bond, basically metal wire, which connects the outside lid, and then they fill it up with some resin mold or some plastic material. Now, usually we do not model all these things, and it works nicely as we have seen in our UG labs. But at high frequency, we cannot follow the same procedure. The simple lid, it is associated with lead inductance. This is basically similar to the self-inductance of a metal wire. And this inductance, is it not present here? It is still there. But we don't face any problem at low frequency because of a small inductor. But we face problem at gigahertz frequencies. Let us take one example. Let's say because of this lead, so we have a thumb rule actually. Typically, we have 1 nanohenry per 1 millimeter for the wire bond. So anyway, so let us consider for simplicity, we have 1 nanohenry of lead inductance left side. Similarly, we have another 1 nanohenry right side. Now, if I calculate the reactance due to 1 nanohenry at 1 megahertz, how much it is coming? Omega into L. So twice pi into 10 to the power minus 6 into 10 to the power, 10 to the power plus 6 into 10 to the power minus 9. So it's in milliohm. But if I go up even at 1 gigahertz, so 10 to the power plus 9 into 10 to the power minus 9, already above 6 ohm. Now, if I consider 30 gigahertz, so 6 multiplied by 30, it is more than 180 ohm from left side, another 180 from right side, and compared to 50 ohm. So it's very high. If I use a diode with this type of plate, simply my microwave power, it won't enter the device. It will be reflected back from the lead. Sorry. So we use some modification. So first straightforward approach that you try to decrease this value by changing your configuration. So here is one example of fabrication of a register, and mostly we use QFN package. Yeah, here I have a picture of QFN package. So top right, you see, these are the microwave components, not even millimeter wave. So at 24 gigahertz also they are available. So these are resistors or capacitors. Here actually I'm showing resistors, and look at their size. So the very first thing they did, decrease their size. Then they did not use any wire as the lead. It is just a metal plate for connection. We call it QFN packaging. And right side it's showing it is the same thing for one IC. So this is microwave IC, where low frequency IC left side it looks like this. So for microwave IC, you see, these are the leads externally available for integrating to PCB. And the middle one, this is the bottom view, and here this one is the top view. So it looks different. So that's how they can decrease it, but they cannot avoid it completely. So in fact, these SMT components, let's say like resistor, capacitor, we could still use with their appropriate model at 24 gigahertz in our circuit. But when we are trying above 30 gigahertz, it is creating problems. Not that we don't have the model. We have measurement facilities, we can generate the model, but because of problem like this, how I was explaining here, so it may not be now 1 nanohenry, a fraction of nanohenry, 0.2, 0.3 nanohenry, but that still provides significant reactance. So here is one example of the model of a equivalent model of a SMT register. This is the low frequency model, this is the high frequency model. But modeling is fine. We do not have any problem with the model, but because of this high inductance value or high capacitance value, so it is not high. Let me correct my language. The numerical figure it remains same, but because of this, the equivalent reactance becomes so high, then use of SMT components at millimeter wave frequencies, it becomes questionable. Particularly, let's say you are trying to do something at 77 gigahertz, no SMT component. Only option, you go for RFIC or MMIC. So in MMIC, it is much smaller. So we can avoid this reactive part, means to great extent. It will further down. Well, now how we connect it to PCB. So this is a beard die, and this is the picture taken just after connecting the wire bond to outside. So this die is placed on a ceramic base, first of all, with some backside metallization. And then these are the metal metal lines. So it looks like microstrip line. And this is connected to the outside lead, which are again metal pads like this. So these are the outside leads, metal pads for connection. So this is with the wire bonds. Now, obviously, all these pins, they are not associated with gigahertz frequencies. Some of them are for biasing, some of them just to control the chip. So kilohertz, megahertz to DC. Only few pins will be associated with millimeter wave, and for those pins we have to take utmost care. So here, if time permits, we'll discuss about this wire bond. What should be the shape and type of wire bonds to decrease this inductance at millimeter wave frequencies. So once it is done, then they will be using some covering, some material for covering for packaging. Packaging is a huge topic. Anyway, so for now, this the moment I introduce any any dielectric material for packaging, then it will create other problem, other challenges. So packaging material is basically a lossy dielectric. Then power will be coupled to dielectric material, and it can give rise to surface wave mode. So surface wave mode it is another it creates another challenge. How we can avoid it? So the surface wave mode, it will absorb power, and actual operation of the chip, it will be interrupted. So packaging material or the physical volume, we need to model it using a full wave simulator. So the conclusion for now is that packaging itself is not a separate design anymore at millimeter wave frequencies. We need to model it as a part of my design using any EM solver. So this is an example of a smartphone PCB. So only one of them dealing with gigahertz frequencies. Well, last one, waveguide. So if you go and study about different guiding structures, you will see that waveguide provides least loss among all the guiding structures, particularly air-filled rectangular waveguide. So that's why people prefer waveguide, but when you go for a low loss application. So these are some waveguide based components. Amplifiers, you can identify it is WR10 for W band application. So the width is just 2.5 millimeter. This is the waveguide input feed, and these points are for biasing. This is a circulator, and top right, it is one dish antenna. So you can identify this feed structure. Now, when we design dish antenna, polishing of this antenna, it is a problem. The problem comes due to the surface roughness, as I was discussing. Otherwise, antenna efficiency will decrease significantly. So this polishing, again, it is a challenge, and it is actually expensive procedure. Here are some more waveguide based antennas. Well, so before coming to next topic, better let us take a few questions. So you can, we don't have many numbers of participants. So if you have a question, you can switch on your microphone and ask me, please.
Yes, dear participants, you have any queries, you please unmute yourself and you can ask questions.
And even the participants are free to post their questions in the chat box also.
So no question. Okay, I am asking you one question. How many of you designing at millimeter wave frequencies? Any one of you? And what type of design you are involved in? Any participant working at millimeter wave frequency range? Let's say for 5G or anything else? I did not understand the term NDT. You can unmute.
Mr. Shankar, you can unmute yourself. It is non-destructive testing. He has written non-destructive testing, sir.
Okay, non-destructive testing of what? Some biological tissue material or anything else?
Non-destructive
fine.
testing of dielectric materials.
This is like a general thing. Anyway, anyone else? Anyone working on some design related problem? It can be antenna, passive components, RFIC, MMIC, anything. None of you. Okay, one of you wrote antenna. So for what type of application? Do you have any application in your mind? So why I'm asking, because then while presenting, I can cover those points. So don't be shy. Yeah, DOA, it's a completely different topic. Today, we are mostly discussing about the design and implementation issues. Okay, antennas for 5G. Well, then I would cover also some of the antenna related problem. Let's see. Okay, thank you then. So let me start with the material. So what type of materials, let's say, is suitable for your application? So mostly I'm going to discuss these points from circuit point of view. And of course, let's see if I can cover some parts of the antennas. Well, the very first challenge we face at higher millimeter wave frequency range and at terahertz frequency range is how to characterize the material. So one of you already said that you are measuring some dielectric materials, and permittivity, it is a complex quantity, and both the real and imaginary part, they are function of frequency. So how we can measure them correctly? Unless we know their exact values, then after fabrication, we will be facing problem. So see, at the low frequency, usually we don't face as such any problem. These are some common methods I wrote here: parallel plate capacitor method, or transmission line method, or resonance method. Now, at high millimeter wave frequencies, let's say above 100 gigahertz till almost 10 terahertz, people use terahertz time domain spectroscopy for material characterization. So mostly we are interested in the electrical parameters. Means what is the sigma, how it varies with frequency. So sigma, it is also a function of frequency. Then what about the real and imaginary part of permittivity? So this type of materials, sorry, this type of parameters. And we cannot determine them very accurately. That creates a problem. At high frequency, IR range, or visible wavelength, again we can determine them correctly. So this is popularly known as terahertz gap. So unless you are going for measurement, you are not sure finally it is working in the desired band or not. It is true for antenna. Also, it is true for any passive components. Because material property, it determines the change of phase, attenuation, all these parameters, right? Now, let us revisit the popular substrates which we frequently use for microwave components particularly. So here I am just giving one example, AICTE-ISTE 5880 and 5870. So these are available from Rogers Corporation, and they suggested they actually characterize it over 8 to 40 gigahertz. Above 40 gigahertz, no data is available. So can I use the same material at 77 gigahertz? Then what is the dielectric constant or what is the loss tangent? At least Roger, they are not providing any data. I'll show you some examples. Some university groups, they tried to use those popular materials, mostly popular at the microwave frequencies. And this is one of the excellent materials available from Rogers Corporation with a loss tangent of 0.9 at 10 gigahertz. So these are the electrical parameters. When we go for practical implementation, other than the electrical parameters, we need to also consider some other parameters, like what is the tensile modulus. So basically mechanical rigidity, then temperature variation. So if we change the temperature, dielectric constant, again, it is a function of temperature, and the same is true for sigma. Then what is the vapor absorption coefficient? So depending on all this, so we have some space certified material. So that also we need to keep in mind. Otherwise, even after fabrication, finally, it is not useful for system integration in practical field. So that we are not we are not including those parameters in our simulator, but we need to keep those points in mind while going for implementation. Now, coming back to these popular materials, AICTE-ISTE 6006 or 5880. So some university groups, they characterize it at higher frequencies. So for example, one group, they are reporting a measured result for AICTE-ISTE 6006 at 10 gigahertz from Rogers dataset. It is 6.2 and loss tangent 0.002. And at 100 gigahertz, they are saying that mostly it's epsilon r is changing to 7.4. But this is actually, I doubt, loss tangent, they are saying it remains same. Theoretically, if the imaginary part, the loss tangent is mostly determined by the imaginary part of permittivity. If it does not vary with frequency, then loss tangent should decrease with frequency, if you look at the expression. But practically what we see, this epsilon double dashed, imaginary part, it increases with frequency. And that's why loss tangent, it increases with frequency. So for AICTE-ISTE 5880, another group reporting that its epsilon r is slightly changed to 2.24, but loss tangent, it increases to 0.004. Quartz, it's a very popular substrate for higher end of millimeter wave or sub-millimeter wave frequency range. It is an excellent material, but fabrication is a problem. So loss, you look at the loss tangent value, it is just 0.0002 with epsilon r 3.8 at 100 gigahertz. Now I'm showing one measurement result. So here what they did, they fabricated one microstrip line on a 35 NQ substrate. It's one organic based dielectric material of length 20 millimeter, and over they are measuring it over 1 to 60 gigahertz. So 1 to 60 gigahertz, if I look at S21, S11 was below 25 dB throughout this range, so negligibly small. Now look at S21. At 1 gigahertz, it is just 0.1 or 0.2 dB. At 60 gigahertz, that increases to 40 dB. So less than 50% power is available just after 2 centimeter. So why? We have several sources of loss, and all these loss components, they are frequency dependent. They increase with frequency. So we have high conductor loss, dielectric loss, as well as surface wave loss. So here they chose the substrate thickness in a way so that power lost in the surface wave remains less than 5%. So then just because of conductor loss and dielectric loss, you see, less than 50% power is available at port 2. So this issue we have to keep in mind. We cannot use long lines at millimeter wave frequencies, particularly PCB based line. They are lossy. We cannot avoid that loss. Some other popular materials, alumina. This is the most common material, not just at millimeter wave, even at terahertz frequencies. And depending on purity, epsilon, it varies from 9.6 to 9.9. It has excellent loss tangent. Even at 100 gigahertz, it's very close to this. Another popular material is quartz, as I said. So we have different quartz material, but here fabrication is challenging. Otherwise, it is an excellent material. And again, they are also used at terahertz frequencies. So because of low loss tangent, you can compare the loss tangent values. Some other materials are also listed, but they are not frequently used, of course. Now, since alumina is the most popular material, let me show some of its basic parameters, how it varies. So left-hand side, it is refractive index, and you know that refractive index is proportional to square root of epsilon r. So from here, we have some information how the dielectric constant it varies with frequency. So we are considering the millimeter wave, whole millimeter wave frequency range till 2.5 terahertz. And they plotted it. This is the measured result for two alumina, one with purity 96%, another one with purity 99.6%. And right side, it is the absorption coefficient. So basically alpha per millimeter. So for purity 99.6%, you see, even at 2.5 terahertz, we have absorption of just 1 per millimeter. But of course, it increases with the impure alumina. So purity, it plays an important role. And dielectric variation of dielectric constant also, it's negligibly small. Here the frequency scale is very wide. So it's millimeter to 2.5 terahertz. So this is the reason why alumina is so popular, even at terahertz frequency, and it is not that expensive like other materials. Now, coming to semiconductor materials, particularly we'll be designing RFIC and MMIC. So here I did not include the materials popular for CMOS. So for semiconductor materials, it is very close to dielectric material, and sigma for intrinsic semiconductor, sigma is low. Now sigma increases as we increase the doping concentration. So that in silicon germanium technology, where doping concentration is very low, it is almost like intrinsic material. Rho, it is of the order, rho is the resistivity, 2 kilo ohm to 200 kilo ohm per centimeter at 10 gigahertz, and with epsilon r 12, and that changes to 11.7 at 140 gigahertz with the rho value 8 into 10 to the power 3 ohm per centimeter. Loss tangent also still acceptable, 0.013. It is high, but still acceptable. Now, this is not the conventional silicon used in CMOS. As I said, these RFIC people, they start the fabrication with lightly doped p-type or n-type material. And for them, rho value is much lower. How? How small? It is just 50 to 100 ohm centimeter, much lower. So we end up with high loss. So if we do not go for this high resistivity silicon, this technology, that then you need to keep in mind that if I use the conventional CMOS technology for any RFIC design, even above X band, we end up with a very high loss, and we cannot avoid it. So with that also, people now successful to design amplifier even at 60 gigahertz in CMOS technology. Whereas for gallium arsenide, we have the advantage that rho is very high, 10 to the power 7 to 10 to the power 9 ohm centimeter at 10 gigahertz, and which is 7.8 to 10 to the power 7 ohm centimeter at 140 gigahertz. And also loss tangent value is smaller, particularly at higher frequencies. So we do not face as such any problem due to sigma conduction loss. So it is very close to dielectric material. So that is another reason actually, other than the mobility, why gallium arsenide is so popular. And it is not anything new. People using it over last 30-40 years. This gallium arsenide technology for millimeter wave circuits. But usually they are power hungry and fabrication also expensive. Okay, design steps maybe I come later. Now, sources of loss. As I said that all the losses increasing with frequencies. So you need to know then what are the sources of loss, and then we'll discuss, if possible, how to decrease this loss or to keep below some specified value. Let us consider a general scenario, particularly PCB-based structure or a MMIC structure. Then we mostly face three sources of loss. The first one is ohmic loss or conductor loss. It is nothing but joule heating. So even if I use a pure dielectric material, we need to use some sort of metal to guide the wave. We concept the microstrip line. So for microstrip line, on top we have the metal strip, below we have the ground. Then the moment I introduce some metal, we'll end up with some JS on the metal surface, and we have conductor loss. We cannot avoid it. So what we can do, we can change our configuration, or we can choose the appropriate guiding structure so that this JS excitation is minimum. And as you can recall, JS, it depends on the tangential magnetic field value, N cross H, that is equal to JS. So then when we are selecting guiding structure, or we are optimizing the cross-sectional shape of guiding structure, you need to be careful about the tangential magnetic field on metal surface. That's how you can minimize metal loss. And this is the most important. Why? Because here loss is proportional to square of current component. So if you can decrease the current by half, you can decrease the loss to 1/4, conductor loss. Next is the dielectric loss. So, okay, for the conductor loss, one more point I did not discuss, sorry. So that surface roughness, problem due to surface roughness. This one zoomed in photograph of a PCB material. It's showing the top layer of copper. So how it looks, you see, it is not a smooth surface at all. And typically, if I consider the RMS value of surface roughness, it is 0.3 to 0.5 micrometer. In silicon technology, usually it is much lower, below 0.1 micrometer. But in PCB technology, it is high. So if I go through some polishing, we even after that we cannot decrease below 0.1 micrometer. Now, what is the problem we face? Now, let's say current is flowing on this surface, and then the path length it increases, so we have high resistance. So let me give you some numerical example using the closed form expression. So alpha C, the attenuation constant due to conductor loss only. This is expressed by this relationship for a microstrip line, considering a smooth surface. So it depends on frequency, width of the line, skin depth of the metal we are using to realize the microstrip line. And this is the expression for rectangular waveguide. So this expression even available in DM Pojar's book. So similarly, it also depends on surface resistance, the dimension, and here eta, intrinsic impedance. Now, again, this closed form expression, this is for smooth surface. Now, instead of smooth surface, if we have a surface roughness, let's say represented by capital delta, this is the RMS value of surface roughness, then we need to correct this alpha C by this factor. We need to add this term, alpha C multiplied by twice pi, 2 by pi, tan inverse 1.4 into capital delta by small delta S squared. So when small delta S is comparable to capital delta, then we cannot avoid this second term. And as a result, conduction loss, it increases. So here I'm plotting alpha C for the rectangular waveguide using this closed form expression only. So for smooth surface, according to this expression, this is for the standard waveguide over 300 to 400 gigahertz. It's showing maybe 0.5 to 0.6 dB per millimeter loss, and it increases almost by 2 times when we consider a surface roughness of 0.2 micrometer. And this 0.2 micrometer also easily or it won't come after polishing the waveguide. And polishing inside a narrow waveguide, it's almost impossible. Anyway, so these points we need to keep in mind while going for implementation. Next, the dielectric loss. So the basic theory already you know that permittivity, it is represented by epsilon dash minus j epsilon double dash. Now, if I consider a monochromatic plane wave propagating through this medium and use the Maxwell's curl equation, curl of H, then considering E equal to E naught into j e to the power j omega t, we have these terms. Now we separate the real and imaginary term. Now then the loss tangent, it is defined by the lossy reaction by lossless reactions. So sigma already we know, because of this we end up with loss. So here then the real quantity omega epsilon double dash, it will also give me some loss. And we see that it is due to the imaginary part of permittivity. So when we put this here, it comes this. So if I check carefully this expression, and if I assume epsilon double dash and epsilon dash, they are not function of frequency, then actually loss tangent, it is decreasing with frequency. Here, this is plus something. So it is decreasing with frequency. But practically, for most of the cases, it increases because epsilon double dash, it increases with frequency. Anyway, so similarly, we can also define for the permeability. So here the dielectric loss, it depends on the epsilon double dash value as well as on the electric field concentration. So as we increase the electric field, then this loss part will increase. We can predict that from this expression as well. And it also depends on omega. Other sources, radiation and surface wave loss. So if I take a straight microstrip line, and if the supporting mode is approximately, let's say TEM mode, we call it quasi TEM, it should not radiate. So there is a misconception sometimes. Whenever we have some fringing field in air, we call it is radiating. No, that is not the case. You are not considering the basic condition of radiation. So electric field and magnetic field, they should be in the same phase, right? From our UG knowledge. Otherwise, that cannot propagate through medium. You can consider the case of one inductor or capacitor. For inductor and capacitor, we use the concept of current and voltage. So for a microwave resonator, let us consider the electric field and magnetic field. They are in phase quadrature. So that stores energy. It does not radiate. So in the fringing field is not the only necessary condition. You need to also check what is the phase difference between the electric field and magnetic field. So anyway, a straight microstrip line or a straight CPW line as such, it does not radiate anything. And for millimeter wave designing, we are not going to use long microstrip line. So then radiation comes from where? It comes from the higher order modes created at the discontinuities. So what is discontinuity? As I said, if I use one open stub, let's say, so okay, I can plot it. It will take some time. So if you have any question or confusion, you can ask me. So if you do not ask, I simply skip those things. So why, let's say, one open stub should radiate? So similarly, shorted stub or one impedance step or cross junction or T junction, basically any junction, then any bend, it can be 90-degree bend or anything else. So not just microstrip line, it is for any semi-open structure like coplanar strip line, coplanar waveguide, that is true. And at the discontinuities, since we have Faraday mode, some of them may radiate. So in fact, we have a special antenna, a leaky wave antenna, where we utilize this leakage to direct them in one direction so that we can use them as an effective antenna. One example is you take a long microstrip line and you use periodic open stub, nothing else, just periodic open stub, maybe 10, 20 or 40, and it will behave like a very good antenna. So the moment we introduce some discontinuity, we have to be very careful. It can radiate easily. And we cannot avoid discontinuity when we go for any system implementation or designing any component. Other than that, another important point is surface wave. So this point we need to discuss little in detail because it is one very important parameter. And if you do not choose the PCB parameters wisely, you will end up with losing power almost all into surface wave. So this surface wave, even at lower frequencies, it is still present. So what is surface wave? It actually a special wave, usually TE or TM type wave, which follows the surface of your PCB structure, and it propagates in two-dimensional all over your circuit, all over your dielectric slab. So after this, we are going to discuss it in details. And because of this surface wave, not only that we have power loss, it also creates other problem, like at the end of the substrate where it faces air dielectric boundary, a part can radiate, which is basically undesired radiation, and where we do not have as such any control. So you are implementing a patch antenna on a thick substrate where you have this surface wave effect, and your side lobe levels, cross pole level, all will deteriorate, and you do not have any control over it. So even for one antenna also, it creates a problem. Second problem, let's say you have two components, one component here, another component few millimeter away, but there cannot be a straightforward coupling, near field coupling through air. But because of the surface wave power, it can reach your second component, not even 1 millimeter. Let's say one component at one end and the second component is in the far end. There also we can have coupling through surface wave. So crosstalk will increase. You see, it is because of surface wave, we don't face only just one problem, series of problems. And to only way to keep surface wave excitation to minimum is that you decrease your thickness of the substrate. So h by lambda naught, where h is the thickness of the substrate, compared to the operating wavelength, it should be much less than 1. Similarly, packaging. So if you do not model these packaging materials properly in your EM solver, then even you can consider, let's say you are using simply designing a patch antenna. Now, if you use some dielectric coating, then effective dielectric constant will change for your patch as well as for the microstrip line feed. And if epsilon R changes, resonant frequency will be different. And other than that, if this dielectric coating is too thick, we can have surface wave excitation in that. So the materials used for almost all types of packaging, they are modeled by lossy dielectric with very high loss tangent values. So we end up with surface wave excitation and high loss. So again, we need to be careful about that. Well, so here actually I'm showing the a typical surface wave. It propagates through a surface. It is the cross section of a two-dimensional dielectric slab, and here this slab, without any metallization, it can support both TM type mode and TE type modes. Actually, if you recall from our UG knowledge, we learned that whenever we face dielectric boundary, we have hybrid modes. So that means the propagating electromagnetic wave, it has both the electric field components and magnetic field components in the direction of propagation. So then if I want to model in this case, so ideally we need to deal with all the 6 components of fields. Ex, Ey, Ez for the electric field, similarly Hx, Hy, Hz for the magnetic field. So we cannot avoid any one of them. Now, if I look at the most significant field components, some field components, they are very small compared to other values. So in fact, using the same concept for a microstrip line, we call it TEM mode, but actually it is hybrid mode. But the component of electric field or magnetic field in the direction of propagation, it is vanishingly small. So that's why simply we neglect that and approximate it by TEM mode. And to avoid any ambiguity, we better use the term quasi-TEM mode. Here also we have the same problem. It is not purely TM or purely TE, but if I consider the dominant field components, it looks like TM or TE modes. Sometimes people use some different terms and they are actually mostly popular for the surface wave. So TM modes, it is sometimes called simply E mode when the electric field is parallel to plane of incidence. So here, this is the plane of incidence. According to my picture, Z, I consider it is the propagation direction. So YZ, this is the plane of incidence. Then we have here the dominant field components of electric field are EY and EZ. We have a perpendicular components and in the direction of propagation. And magnetic fields on the HX component, which is again perpendicular to direction of propagation. So this is called the E modes, and the second one, it is called the M modes. So it is not exactly like then the TE or TM mode like a rectangular waveguide. So for M mode, H is parallel to the plane of incidence. So we have then Ex, Hy, and Hz components. And obviously, along with this, it will satisfy this relationship between the propagation constant and attenuation constant according to this equation. Now, in air, if I plot these field components, they decay exponential. Well, so let us consider just one case. Let's say dielectric slab with TM mode. Maybe I can skip this part. If you are interested, you just let me know later, and then I would cover this part. So let me consider the microstrip line case. So this is for the dielectric slab. What we see in general that we have both TM modes and TE modes. And now look at their characteristics. We have here two modes we call TM0 and TE0 mode, and they do not have any cutoff frequency. They can even exist at kilohertz frequency range. But when the thickness of dielectric slab is much less compared to lambda naught, then the coupling window, so coupling window basically the thickness of the dielectric slab, it is so small that an excitation of this mode is negligibly small. We simply neglect it, even at lower frequencies, lower microwave frequencies. But when you are going up, then you cannot neglect it. And other than this TM0 and TE0 mode, this is the expression. We can calculate the cutoff frequency from this expression for in general TM M mode and TE M mode. Yeah, so let me better discuss this one. Surface wave in a grounded dielectric slab. So this dielectric slab, it is with some ground plane metallization. And why it is important? Because microstrip line fabrication, it looks like this. For microstrip line, always we have some metal backing. And that is also true for ground back CPW line. So in many cases, ground back CPW line is also popular. Now, according to my reference frame, Z is the propagation direction. Again, according to the previous definition of TM mode and TE mode, here also actually we have hybrid modes, but we can approximate it by TM and TE modes. So among them, TM0 mode is of particular interest. So in general, for the TM modes, these are the dominant field components. So here the plane of incidence is ZX. So then we have EX component and EZ component. So EX is perpendicular to direction of propagation, and Z is the propagation direction. So we have EZ component, and for the magnetic field we have HY component. Now coming here, without going through any expression, see on the metal surface we cannot have any tangential field. So that means on the metal surface we cannot have EZ component and another perpendicular EY component, but we can have EX component that is supported by this boundary condition. Right now, looking here, EZ within this dielectric 0 to D, how it varies? It varies sinusoidally. This is the phase constant, e to the power minus j beta j in the propagation direction. So some constant, then we have a sinusoidal function of x, and at x equal to 0, it is 0, because it is coming from the boundary condition actually. So it is satisfied by the boundary condition. Now, as I go up, it is sinusoidal function, it increases. Ez is maximum on the interface. And what about in air? In air, now we need to use the second expression. So here we have one additional term, this exponential factor. So it decays exponential. In air, then it decays exponential. What about the EX component? EX, it is sinusoidal. Another interesting thing, we have a 90-degree phase difference between EX and EJ. So for the EX component, it is now cosine. At x equal to 0, then it is highest. As we go up, it decreases. Basically, it is converted to EZ component. And then in air, it further decreases. So EX component, it is maximum on the ground. Now, if I print a microstrip line in the same propagation direction, so power, it's flowing down the line in Z direction. Now, if microstrip line is on top of this, then what about the electric field? It will perpendicular to metal strip and ground. So it will be like this, right? So it will be like this for the microstrip line, and it's quasi TEM. And what about the magnetic field that surrounds this strip, and it forms loop? I have a picture. Let me show you. If any one of you don't remember the field configuration for microstrip line. So this is the field configuration, but here it's on a different plane. This time it is on a cross-sectional plane. So you see, then just below the strip, we have perpendicular component. This is that EX component. Now, if I go back here for the TM mode, so this perpendicular component or EX component of microstrip line will couple power to surface wave through this EX component. And as the thickness is more, then it provides a higher coupling window. It can couple power through much wider section. Then we have more surface wave excitation. So for microstrip line, then TM mode, it creates a problem. Now some other characteristics. Here also we have a TM not mode with no cutoff frequency. And for other higher order TM mode, the cutoff frequency is given by this expression. So it depends on the thickness of that material and epsilon r. So instead of just thickness, it is better to use the term effective thickness of the substrate. And how we define the effective thickness? It is d into square root of epsilon r. D into square root of epsilon r. So if we have the same thickness, let's say 1 millimeter, for one dielectric with the dielectric constant 2.2, another dielectric with dielectric constant 10.2, even though their thicknesses are same, but the 10.2 dielectric will have more surface wave excitation. So that is why we need to use the effective thickness, because it will have higher coupling window. And we cannot avoid TM not mode. Even at megahertz frequencies, TM not mode is there. But coupling window is so small that crosstalk effect will be, you cannot actually notice as such any crosstalk effect at megahertz frequencies. But at gigahertz, we can. And in fact, I do not have a plot. In fact, let me describe it better. Let's say you are designing or implementing a band pass filter. So a simple band pass filter like this, top right, using half wavelength resonator. This is at millimeter wave frequencies. So let's say you are doing it at 2.4 lower microwave frequency. Now many of you did it already, and did you check what is the maximum rejection you could achieve in the stop band? I'm considering far away from the pass band. So at low frequency, you can go to a very good value using very means higher order filter to 70, 80 dB. So I never saw actually in our lab more than 70 dB attenuation in the stop band of a band pass filter in microstrip line technology. Now you try to do it in X band, you want to achieve 70 dB, 50 dB, maximum 60 dB if you choose wisely that substrate parameter. This is because of the surface wave only. So you see, in most of the cases, you simply avoid surface wave. Now, when we are speaking about the surface wave, and since we have seen that we cannot avoid power coupling to TM0 mode, now you have power leakage through from port 1 to port 2, even in the stop band, in the form of surface wave, and you cannot go to a good value below 60 or 70 dB at low frequency, and at millimeter wave, it is very high. So below 40 dB, even it is challenging at 24 gigahertz, not even at 30. So this type of problem you'll be facing due to surface wave. Now, if I do it in some technology where we do not have the surface wave problem at all, one example is rectangular waveguide. Rectangular waveguide is a closed structure. So if I design resonators based on waveguide, we are not expecting any surface wave. It's a closed structure. So in fact, since no surface wave is present for rectangular waveguide, you'll be surprised to know it can easily provide a rejection more than 100 dB in measurement, more than 100 dB in the stop band, which is simply not possible just because of this surface wave in PCB technology. So this is one of the most important issues. Well, so you need to choose the substrate thickness wisely. So similarly, we have the problem due to TE mode, but here the field configurations are different, and it creates problem mostly for the CPW line, this TE mode. Well, let us again take a few questions. Otherwise, I'm discussing. Yeah, so just one point. So how to improve the effect of surface wave? We need to stop somehow this electric EM propagation through surface wave. Then for the TM0 mode, what we have seen, what are the dominant modes here? So dominant electric field, EZ and EX. EX is perpendicular. So if I introduce some metal wire, then EX would become tangential to those metal wires and it will be attenuated by the metal wires. And what about EZ then? EZ, it is highest on the surface. So I can use some additional metal strip, then EZ would become parallel to the strips and it will be attenuated. So that's how they came up with this solution. Use some metal strip, and these are metal vias to attenuate both the EZ and EX component, perpendicular and parallel to surface component. And even after that, you cannot eliminate surface wave, but at least you can improve the response by 10 to 20 dB by this arrangement. So that's why when you see any millimeter wave components, you'll see always they are using this type of structure, guiding structure, ring-like structure. So it is basically to confine your surface wave so that it cannot disturb other components. Then you'll end up with high crosstalk, particularly when you are designing transceiver, transmitter and receiver in the same PCB. It will create problem. It will, your power amplifier, even a slight leakage to receiver side, it can saturate your low noise amplifier. Well, let us take a few questions then.
So there is one question, sir. So
how to choose? Yes. So this part I would cover a little bit in details later. So for now, only one option is there. You need to reduce the substrate thickness. You can do some study. Actually, there is no straightforward thumb rule like that. So what we do before starting our design, we first complete study on surface wave. It's very simple. You can use any full wave simulator. Let me discuss about the steps. You see, in your simulator, if I simulate a microstrip line section, then if you want to calculate total loss, it is 1 minus magnitude of S21 squared minus magnitude of S11 squared. That will give you total loss. Now in total loss, what are the components are there? Dielectric loss, metal loss, and loss due to surface wave. If it is a straight line, you can avoid radiation. There are almost no radiation from a straight microstrip line. So then, if I can avoid conductor loss, dielectric loss, we end up only with surface wave loss, and you can easily do that in your EM solver. How? For conductor loss 0, do not use any metal, define them as PEC with infinite sigma. Automatically conductor loss part is gone. Now define loss tangent as equal to 0. Dielectric loss part is gone. Then what is remaining in the total loss? Only the surface wave. Now you vary your thickness and complete a study at your midband frequency. Let's say your midband frequency is 77 gigahertz. Take your substrate, put PEC, define as PEC and loss tangent equal to 0. Now change your substrate thickness and plot total loss per unit length. So from that, then you can choose what should be the ideal thickness. Got it? Any other?
Participants have any queries?
Okay, since some of you designing antennas, so I thought in the second half, this part is still remaining for 1 hour. And another 1 hour, I thought I'd be discussing mostly on interconnects and packaging issues. But it seems that no one from RFIC and MMIC. Am I right? Anyone designing on MMIC, RFIC? You write it. Otherwise, I can skip that, and instead, I'll be discussing some challenges for the antennas. Is it okay with you, participants?
Okay, sir. We'll do it.
Yes.
Yeah, so we still have another 5 minutes. If you have any questions, so please. When I'm presenting, you are you can always write your question in the chat window.
Yes, sir. Even you can raise your questions in the afternoon session also, because Professor Mandal sir will be available in the afternoon session also. Okay, thank you, Mandal sir. Okay, sir. We will start the afternoon session at 2 p.m.
Okay, thank you then.
Okay, sir. I
Okay, we'll
request
see you
all the
then.
participants to join the session sharply by 1:50 p.m. Thank you all.